I'm going to check out this Marconi TF2370 Spectrum Analyser. This isn't a full calibration check or anything, just to verify that it works. What we've got here is the two parts of the Spectrum Analyser, the display unit and the RF unit. Down the bottom here is the frequency extender, which takes it up to 1.3 gigahertz, but I don't have the cables to connect that, so we can't demonstrate that for now. On the top is a signal generator, which I'll be using just to demonstrate the Spectrum Analyser. That's not part of it and not included in the sale. So I'll switch the analyzer on now, and it'll take a moment or two for the screen to warm up. You'll see the frequency readout is all working okay, and we should see the graticule appear in a moment. There we go, we've got something on the screen. There's nothing to see at the moment because there's nothing connected, but if I connect this cable, hook that up to the 10 megahertz reference output, we get things on the screen. You can see we've got peaks here, zeros on the left hand side, and we're currently working at 10 megahertz per division. So we've got 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 megahertz there, which is working very nicely. We can change the scale to 5 megahertz per division, 2 megahertz per division. It all seems to work fine. The attenuator is currently set to quite a sensitive range. We can change the attenuation. You can see things disappearing into the noise at the bottom of the screen. So that's the internal reference, which shows that it basically works. If we unplug that now and plug into the signal generator, it'll switch on. There we go. The signal generator is currently set to 0.1 megahertz. If I wind it up, we should be able to see the peak move across the screen. If I reach my hand around this side, so as we go up, 10 megahertz, 20 or 19.1, you can see the peak moves across the screen. You can make it a bit clearer by reducing the attenuation. There we go. So that's working quite nicely. We can crank that all the way up, sorry, to 85, 90, 100 megahertz, no problem at all. We can measure frequencies with this, because if I put it into single sweep mode, then we get a bright line on the screen, and by turning that around we can see where the peak is. So that one there, it's not going to be very accurate because it's 10 megahertz per division. If I put it on the peak, it shows 49 megahertz on the screen. It's 49.1 from the generator. That's close enough for me. Let's try and get it a bit more accurate. If we zoom in somewhat, let's put the center frequency in the middle of the screen for now. So it's gone up there, and bring it back into view. If we put the center frequency in the middle, it makes it easier simply to zoom in and increase the resolution. So that's 10 megahertz, 5 per division, 2 megahertz per division, 1.5, 0.2, 0.1 megahertz per division. And let's get that centered. So that's our signal of 49.1 megahertz. Let's try the bright line test again. I put it on single sweep and put the bright line over it. There we go. Now you can see it's exactly 49.1, and it matches the signal generator. So now we should be able to do some higher resolution measurements with the analyzer. If we add modulation to the signal, we should be able to see that. To do that we need a lot more resolution, so we'll have to change over to kilohertz per division. Let's start with 10 kilohertz per division, make sure we don't lose it. Okay, we've lost lock there, which does happen when you change ranges because it has a different phase locking arrangement. Oops, if I nudge this back on, recover our signal. Hang on, it's not supposed to happen. Oh, there we go. There it is. It's now. Oop. It'll be tricky to get the phase lock to work. It's easy to do this in manual sweep. Let's. There we go. Oh. It sweeps quite slowly. Let's put it on wide bandwidth to get a faster sweep, and then we've got a much better chance of actually finding our signal. Needle in a haystack. We're on 49.1. There it is. That's what we wanted. Now we can search around with the fine controls. Okay, so we'll put the filter back down to normal bandwidth. And you can see it gets quite a lot narrower. And now we want to zoom in. I think, 1 kilohertz per division would be useful. So let's do that. And now the sweep takes really a lot longer because the filter bandwidth is much narrower. There we go. There's our signal. We can center it a bit better on the screen if we do that. Let it sweep again. Oh, wrong way. Oops. There we go. So once we've got it well in view, let's wait for the next sweep. Oh, I keep turning the knob the wrong way. Speed the sweep up. Oh, there we go. There's a fast sweep button. I should have pressed that all along. Okay, let's get that centered nicely. Oh. That'll do. That'll do. Right. Now if we put the filter on narrow bandwidth, we should be able to see that that's just one peak. Works very nicely. And now if I switch modulation AM on the signal generator, 400 Hz will start with AM on. You can see that as the generator or the signal spectrum analyzer sweeps, we can see the modulation sidebands of the signal. So this is a 49.1 megahertz signal modulated with 400 Hz AM, and you can see the modulation. It's not very clean, but that's the signal generator's fault, not the spectrum analyzer's. And we should be able to, if we stop the sweep now, let's just let it finish that. Okay, we should get our bright line. There we go. So the center is at 49.1 megahertz. You can see clearly on the display. And the side bands, first one is at 49.09977, so 400 Hz less, and within the resolution of what we can do with the bright line, it's about 400 Hz higher for the other sideband. Obviously this is a bit approximate because I'm not using a very high resolution. If we start the sweeping again, we can now change the modulation frequency to say a kilohertz, and we should see a different pattern. Oh, there we go. We've got 3 peaks now, and stop the sweep at the end of that. Let it complete. Dum, 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 dum. There we go. We should get our bright line. So the first peak is at 49.1 megahertz. Close to the signal generator can get, and the side bands are at 49.101, so 1 kilohertz higher and 1 kilohertz lower, just like textbooks say they should be. So that's the spectrum analyzer working in action. I haven't shown its full maximum resolution. We're still at 1 kilohertz per division. It goes down to even finer resolutions, which we can have a go at. See what happens. Auto, and let's see. So we're back to our 400 Hz signal. If we go to say 200 Hz per division, let's see if it all stays on screen. Oh, there we go. Now you can see that our 400 Hz signal is roughly 2 divisions apart. 100 Hz per division. It's really testing it now. Scans rather slowly. Is it scanning at all? So 200 Hz per division. And aha, okay, this scale, the bandwidth is so narrow that it takes 100 seconds to sweep, so no wonder we can't see it doing it. Let's put it on a wider one. There we go, just to prove that it works. We've got there's our signal, so we'll put the peak in the middle, and there's our 2 side bands from the amplitude modulation. Put it on, oops, normal sweep. You can speed up the sweep by doing that. There we go. There's a few errors because I'm sweeping quickly, but you should be able to see the side bands in much more detail now. And this is not a bad performance. The frequency of 49.1 megahertz, we're sweeping at 100 Hertz per division, so it's really a great deal of detail we can see in the image. So that completes the test of the Spectrum Analyser, and that demonstrates that it's in working order. Thanks for watching.